welcome everyone to Performance Best Practices from the Extreme Performance series. My name is Valentin. I work in support in Premier Services. I've been with VMware for 10 years, working in resource management for the past 7, 8 years. So just a question in advance, who has been in one of these sessions before last year, the year before? Wow, and you're coming back? Okay, no, it's appreciated, obviously. I don't understand you, but it's appreciated. So that's great. You know the drill. You laugh at all of my jokes that are not funny and entice others. But we have a little bit to cover here today. So I'm going to make it an early start while everyone sits down. There's still one spot in the front, I think. Let's get started. You all have seen the disclaimer. I don't have to go through this. We're not going to talk about anything secret, but if I do and something slips, obviously it's all highly secretive. The talk is inspired by the Performance Best Practices, which is this PDF book. And I'm always going to ask the same question. Who has read the full Performance Best Practices document? Oh, come on. It's going down every year. All right. So it's actually not that big, right? So the last one was released in 2018, and you might say, oh, I just wait for the 7 version, download that, and then not read it. But this was released. It's 1.3 megabytes. It has about 88 pages. And there's about 500 something best practices. Now, I'm not going to go through every single one. I'm not even going to go to a substantial amount of that because that would just be reading out best practices, and that's boring. And the reason why I didn't read that book is exactly the reason why I'm not going to do that, because it's boring. I like the book, but that doesn't mean it's not boring. You should still read it, obviously, because it takes 2 to 3 hours. Don't read it in the car. Read it in the flight back home. It's actually fairly comprehensive. So with that being said, we're not going to go about everything that we usually recommend, right? Reserve your most important VMs, leave hyperthreading enable in the BIOS, account for oversubscription. This is your job to follow up on while reading the performance best practices whenever you're on your way back home and you have some time. What we're trying to concentrate on are a few specific parts of performance best practices to go into depth and to hopefully manage the 88 slides we have ahead of ourselves. Yes, you're in for a race. But there's a few URLs here that you might want to write down. They usually list the relevant resources that you might find interesting as well. And again, this is a fairly general session with some specific examples. So what's the agenda? Power management. Yeah. Okay, so everyone that has been here before, I'm probably talking about power management every single time. And the reason is it is still important. And I'm going to stop covering it when stuff or SRs get escalated to me because of that. So until then, we're going to talk about power management. We do a very quick L1TF review. We're going to do some CPU topology explanations. It's very, very quick. I just want to go into what is CPU topology, what is NUMA topology, what is a VPD and a PPD. And then we're going to go into another topic that's a little bit closer to my heart on is extreme performance always necessary? All right. So power management. Power management is an umbrella term, and everyone here usually thinks power management, didn't that cause me performance issues in the past? Am I not better off turning all of that off? Well, no. First of all, you don't turn it off. You set it to certain factors that might not affect you as much. But power management covers a ton of different stuff. If you go into a BIOS and you look at the power profile, the individual subsettings that are being set by the profile are manifold, right? So there's so many different settings that usually all get bunched up in that term. The ones that usually affect you are P states, performance states, and they have different names. They're called power regulators, CPU power management, enhanced intel speed steps. So it comes with different names, but the proper terminology is performance states. And these usually affect you in the negative. For the most cases, when they're being overzealously used by a heuristic that isn't accurately interpreting the performance needs of the application. And then there's deep C states. You say, ooh, C states, that's something with latency, that's bad, I want that off. Well, yes, it has something to do with latency and higher latency, but that's not always the bad thing. And we're going to go into detail why we actually would have deep C states and why it is a best practice recommendation. So, quick refresher for those of you that have been here before, and for those that have not. A P state is a performance state, is a frequency. And a frequency that is specifically coupled to a specific voltage. So a CPU cannot run at a grade of a frequency from 0 to 2000. It has predefined frequency states that are coupled to a specific voltage. And these are inherent for the processor and the processor type. While the processors are running, while something is executing on the CPU, that's when we have a P state. Something is executing, it runs at a frequency. That is the C0 state, so the non-idle state. Once an idle thread is running and issues halt, the CPU then is idle. It doesn't run anymore, a P state doesn't apply, then we halt while we wait for something to execute again. And those are the C states. And the C states, there are different depths to them, and we're going to cover that in a second. So this is a thermal image of a Nehalem processor with four cores, and on the left-hand side you see it fully running. Obviously, white means hot, so resistance, stuff is energy, pixies are flowing through all the parts of the CPU, and it's heating up. Now, on the right-hand side, you see what a CPU most likely looks like when it is in C1. So idle, whenever the idle thread is running and executing halt, that actually turns off the CPU. On your laptop, on your phone, on ESXi, the ESXi idle threads, parts are being turned off. What is being kept alive are the caches, so that other CPUs can still snoop them and verify correctness between them. So again, a C1 state, stuff turns off. And the distance or the wake-up latency to do a transition from C0 to C1 is 1 microsecond, approximately, right? It differs. But 1 microsecond is quite a bit for a CPU, right? I mean, how much does light travel in a vacuum in 1 nanosecond? So, factor of thousands. This much, right? So 1 microsecond, okay, it's a little bit longer, but it is still a fairly long time for a CPU. Now, we said there are deeper C states. Deeper C states, for example, this year, C6, here you can see that the caches, or the lower order caches, are flushed into higher order caches. So here, the C6 state, actually, most of what remains within that core has been evacuated so that we save more energy. But it also comes at an increased latency, 30 microsecond. And now I say, wow, 30 microsecond, that's a very long time. Of course, I don't want deep C states, because look at that latency. So how about I clap, and then you count to 30 microseconds, and you clap again. So it is a long time for a CPU, but it's not a long time, right? So any overhead is only as bad as how often it is being realized. If you don't go into that deep state very often, right, and if there isn't anything that has to wake up as fast, so if you don't have a wake-up latency-sensitive application, this doesn't really matter too much, right? It all matters on how much time you spend in that transitioning phase. If you go to idle, you sleep a while, you come back out, you're good. If you have to wake up every single time you go to sleep really quickly, obviously there's a problem, but luckily most workloads don't behave like that. Most, 95%-ish. All right, so this is an overview that I put into Excel of the different power management profiles of a Dell recent-ish generation. So we recognize some of the words that are different than P states and C states there. And all of these things, take your time, take a picture. Actually, I think there's a mistake in there, so I'm not going to tell you where. I'll buy you a beer if you find it. Okay, actually, but only the first 2 or 3 people, else it's going to get expensive. But so we see many of these terms here, and what we can see is that the different profiles set different settings. So a profile doesn't just affect P states and C states, it affects many other things that we maybe not even see on this particular page. So when people say, I'm just going to set it to performance or set it to custom, then maybe you're not realizing that you're setting settings that affect the host in different ways than just P states and C states. So what you see in ESXi, and you say, well, in ESXi I can control power management, right? No, yes. You can control the power management that the host allows you to control. Depending on what you set in the BIOS, you have different technologies being presented to ESXi, and then ESXi will do something based on its policy. So you effectively have 2 policies running in front of each other, and ESXi can only do something with the things that it gets. And what we see here is, under technology, are the technologies that are being presented, and the policy is what it does with those technologies. Now there is so this balance there, or high performance or whatever you configure, that doesn't just go away. Because just because the BIOS doesn't present C states and P states, doesn't mean we cannot still have a configured power management profile. But in the past, you might have seen not supported there. I think that was phased out in 6.0. Because we thought maybe we do different things with the power management profile besides just P states and C states. So how the control flow works, right? The and this is a very reduced screen, a very reduced example of all the different ways that the systems interact, but the BIOS has to present P state and C state to ESXi so that ESXi can then run its idle threads, and it can run its idle threads to the depth that it needs, and it also sets the P states. And usually it devotes the P states, it writes them directly into an MSR and say, you run at this frequency, you run at this frequency. And during the balanced policy, usually if the requirement goes above a certain very low threshold, we immediately ask for full frequency, full performance. Sometimes, well, not sometimes, but when P states are controlled by the heuristic and the BIOS, it's fairly, how can I say this nicely? It's underwhelming how fast it reacts to load changes. And sometimes it only reacts to the aggregate or the average of the demand of a socket and then sets frequencies on those cores. So fairly often you're running at too little of a frequency when you leave the BIOS control it on a dynamic policy. The important thing is a guest can halt, so it runs its idle threads, it executes halt, but that halt doesn't stop the CPU. What would happen if a guest could halt and stop the underlying physical CPU? Well, then you couldn't overcommit, right? So what happens is once a guest executes halt, the monitor traps it, we tell the VM kernel, and we deschedule the vCPU until it wakes up again, until an event is triggered. So again, guests halt, but that halt never reaches the CPU. The idle threads of the ESXi is what reaches the CPU. And here we want to idle deep when we can, and for reasons that we're going to go into in a little bit. So again, this is the part that's relevant. The rest, not as much. So, as I said before, let's look at a specific subsetting of a Dell system, and it's called the system profile. And in the system profile, we can select the power management policy. Performance per watt, which is the default in most shipping systems. Performance per watt OS, which some people might select because they heard that you have to configure OS control instead of high performance, but that's only half of the story. Performance, dense configuration, and custom. Now these four profiles will set different things. If you look at CPU power management, if you set performance per watt, it will be system DPN, demand-based power management. If you set it to performance per watt, it will default to OS. Basically, lets the OS control the P states. And then we have maximum performance, which is the BIOS completely runs at P0 at the highest frequency at all times. Then we obviously have C states, but that's fairly simple on Dell. It's enabled or disabled, whereas on HP, you can select the deepest possible P state you want to go. And they should probably select C6 retention. But this is what is being set by those profiles. And we are only showing you, or I'm only showing you C states and P states here. There is a ton of settings, imagine going down the list here, and there's a ton of other settings that is being set by that profile. Okay? So this is just the ones that we look into because they affect ESXi specifically, but there's tons of other stuff. So which of these CPU power management features will end up presenting P states to ESXi? Don't be shy. 1, 2, all 3? Okay, fair enough. I mean, I went to a pub, you probably didn't, you're shy, it's okay. So it's just the middle one. Just the middle one will end up presenting P states to the ESXi. How about for C states? Come on, it's enabled, disabled. So only in this configuration, when we have OSDPM and enabled C states or P states, the technology will represent it. But the effect of system DPM maximum performance are completely different. System DPN will use its own heuristic to calculate the P state for you and force you to run at it, whereas maximum performance will always run at the fastest frequency. But this is how P states get passed through. Now on ESXi, based on what we just learned, if we look at power management and we see technology only C states, what do we have configured in the BIOS? So what we've configured is most likely dynamic, right? Because we don't see P states, because P states are being controlled by the BIOS, and C states are still presented. If we see nothing, yes, performance, very good. So here, because C states are not presented and P states are not presented, we're most likely running performance in a performance profile. Now this doesn't guarantee anything because you can set up custom profiles and you don't know what the rest of the options are, but usually when you see nothing there, you're probably on high performance. So once we go into, everyone has used ESXtop or has heard of ESXtop, right? If you haven't, log into an ESXi host, open SSH, type ESXtop, into Google at the same time, I would guess, because it's not very intuitive the first time around. But here we're looking at the power screen, so you press P, and we're looking at a host that is dynamic. And what can we see? We can see that we don't see which P state levels we have, and we can see that we're in a deep C state. So ESXi, you can only see C2 here. Well, in theory, it should be C3 or C6. C2 just means that we're in a deeper C state than C1. But look at APerf, MPerf. APerf, MPerf is the current frequency of the CPU. So right now, it's 50% of the nominal frequency. The nominal frequency being whatever is printed on the box. So C2, we're running in a deep C state. APerf, MPerf frequency, and we're running half the frequency. APerf was introduced in 6.5, and you have to enable it. So you press F, you select the row for APerf, MPerf, and you can see what the frequency of the course is. Let's look at another example. Let's look at performance. We can still see no P states because P states are not being presented and we don't get P state information. But now we see that there is no deep C state and that APerf is at 108. So there's a reason why it's running faster than 100%, which is also the reason why we want deep C states, but we're done talk about that in just a minute. And then here's an example of a host that's configured according to best practices. We have all of the P state information. We're running in a deep C states. We're also running in very high P states. And APerf, MPerf is a little bit more dynamic than it was before. So this is running at the balanced policy. Again, you're saying, well, but why would I ever run at a lower frequency? Now, again, in balanced, we switch very, very, very quickly to the highest possible frequency. This host is basically idle. It's not doing anything. Yet you see that some of these cores are running at a very high P state most of the time. Right? So we are very sensitive to performance. We rather default to performance than we do for energy conservation. 2 letters are turned around. So the reason why we do this, the reason why we want deep C states is that since Sandy Bridge, so for quite a bit, we have turbo boost, meaning dynamic overclocking. That means that in multipliers of the front side bus, in multiplicators, we have turbo bins where we can dynamically overclock the CPU, and that is being done automatically. As long as you run at P0, meaning the highest nominal frequency, the Intel microcode will overclock the CPU for a certain extent. And that's only if I'm in a very low C state, basic halt. If I actually make cores sleep deeper than that, the CPU will overclock the remaining cores even higher. Meaning if you don't have deep C states enabled, and if you don't run with a policy on ESXi that doesn't use deep C states, you will not achieve the maximum frequencies of few cores. You will always have a baseline of turbo bins on all of the cores, like 1, 2, 3, or 4, but you will never reach, so some examples, some CPUs have a range from, let's say, 1 extra gigahertz if only 2 cores are being used extensively. Again, and then the example is the more cores you shut down or put into deeper sleep, the higher the turbo bin output will be for the remaining. All right, so usually here people are saying, well, you know what, I've known about this for the past 8 years. You're a little bit late. Most people actually had problems with dynamic, especially pre-Haswell, because they were running at effectively half the frequency, even if the hosts were completely full. It was a sensible green default, but if the green default causes so much pain, then it often is overridden, and the pendulum swings all the other way into something that is fairly ineffective. With anything Haswell and later, it got better because it introduced per core P states, meaning now you had a voltage plane into every single core, so you could do P states individually for every core instead of just assuming an average of the whole socket, right? So a little bit better. If you have high performance configured, you're good. You're okay. It's not a bad thing. It's a good policy. It's deterministic. But my argument is that the optimum configuration is a custom policy where you have P states and C state controlled by the ESXi. Now, I'm actually willing to argue about the P states because the P states, I run a custom policy where I don't use them at all for some applications, but I want deep C states. The benefit is in a custom policy is you can change those settings via API. What do you have to do if you want to change C states and P states on your Dell system or HB1 manage? You need a reboot, right? Any power management policy that is exposed to ESXi, we can change via API. If you want deep C states, you do them, you enable them. If you realize 10 seconds later that they're no good, you disable them, right? You don't, it's hard to get that flexibility if you don't prepare for it. So now because I've heard this before, I tried your custom policy, it was not as fast as high performance. All right, okay, let me go into that. So if your server started out in a dynamic policy, and what you did is you went into the BIOS and you switched the P states to OS control and you enabled deep C states. What did you forget? The rest of the other settings, right? So we do not go from dynamic to custom, right? We don't do that here, right? So what we do instead, we go dynamic, performance, and then custom. That ensures that all of the other settings besides P states and C states are set to the max performance limit. I can see he's pointing up, so it's just over there. This is the way to do it. All right. So let's just go into some frequently asked questions for power management. Why doesn't the frequency I see in Task Manager change? I get that, well, I used to get that once a week. First of all, you're looking in the wrong place for identifying where the frequency is coming from. And the other possibility is that the guest OS has no way of knowing. Now, if you look into Task Manager there, I have to disappoint you. We're not actually really have a secret CPU that runs at 18 gigahertz. And what you can see down there, the base speed is 2.4 gigahertz and the speed is 2.4. In theory, the base speed is set via CPU ID. So if you call CPU ID with a value of 16 hexadecimal, it returns in the EX buffer the first 16 bits. That is the frequency in hertz. So a little question for the crowd here, another beer. If you have 16 bits, what's the maximum frequency that could be set with this? Oh, no, up. About 65,000, right? 16 bits, come on. Okay, so no beer for anyone here. So here's the thing, right? But I actually did set this. So we can set CPU IDs, we can override everything. Every CPU ID is masked for quite a bit, and you can, in theory, present anything you want. Well, don't do that. Don't take pictures. You're not supposed to set that. That's an example, because you can break stuff. But I actually tried to break it, and it didn't turn out, and I couldn't set it. And the reason is that Task Manager actually looks at SM BIOS instead of CPU ID. Sometimes when you see differences in what you see on the hardware and what you see in the VM, if it pulls information out of SM BIOS, we don't fill that in very well, because we don't need to, because there isn't any reliance on it usually. Rely on CPU ID. SM BIOS is, Okay. So this is normal. If you rely on the frequency in the brand string, that is literally just a string that is being pulled out. So don't rely on that. I turned off all C states. Why is it still showing? Well, as I said before, you don't actually turn off C states. You turn off deep C states. When ESXi wants to idle, it idles. The only way you can turn off C states is if you tell the guest operating system that when it runs its idle thread, it shouldn't use halt. And you can do that in Linux via poll equals idle, idle equals poll. And there's a policy in Windows where you can turn that off. So if you have a VM that is running and it's consuming more, 100%, but it's 90% idle, there's probably something like that going on where it's not using halt. Okay, so this all sounds very complicated and very risky. Isn't it just safe if I do not do anything and just set high performance? And the BIOS, isn't that just the best thing? Well, no, not really, because you can still be impacted. You can still be impacted by PSU redundancy, so one PSU shuts down. You can still be impacted by power capping that is configured accidentally. You can still be affected by temperature and firmware bugs, right? So there is no guarantee that you run at the highest frequency if there's something else going on. But the most important part is you do also not get the ability to control P and C states. When I run experiments, I often want to eliminate turbo boost. Instead of rebooting and disabling it in the BIOS, I just set the P state limit to 99%. No more turbo boost and deterministic results. So if you have an application and you want to figure out whether turbo boost affects that, if you did this, then you wouldn't have to reboot all your hosts. And obviously no maximum turbo boost frequencies. Now I once was asked, where can I find all of this? This is not nowhere documented. It is, you just have to know where to look. What you want to Google for is on the site Intel, you want to look for turbo bins. And usually on the spec update sheets, you see the maximum frequency for the core counts. And just to zoom in a little bit, for a few of these models, the difference between turbo bins without deep C states and turbo bins with deep C states, it's about 500 megahertz. But there's also examples where it goes into the gigahertz range. All right. Anyone done with pictures? Take 20 more. Okay. Oops, actually I already did it. So I can clearly see C2 in perfmon. Didn't I say earlier that guests can only idle and they have no idea what deep C states are? That's right, because perfmon and Windows are lying to you. I don't know whether it's a bug or a specific display issue or choice, but what you're seeing here is simply an operating system that has enlightened functionality. So if you see C2 in perfmon, it's not a deep C state. It won't change the latency at all. It is a feature where Windows, when it's idling and is descheduled, we don't have to wake it up for timer interrupts. You can Google for ITTD, there's a specification. You should never have a reason to disable this, just if you don't believe me and you're skeptical, which you should be. No. You should be skeptical, you should believe me, but you should be skeptical. You can disable that, but you shouldn't have ever a reason to do so. Okay. One more disclaimer before we jump into security. This guy, not a security expert, right? So, because we're going to talk about L1TF, I am a security expert when it comes to the performance of these features, but I'm not talking for the security team. So when I tell you turn it off, what could go wrong, right? Don't complain to Mike about that. Actually, I was running this by a colleague earlier, and he was like, "Your joke is old, and the picture's about 10 kilograms outdated." That's okay. I can take constructive criticism. So instead of telling him his mother's old and it's only 5, I updated the picture. You happy now? All right. Any case, moving on. L1TF. L1TF is also known as foreshadow. Foreshadow never really stuck. But L1TF is everyone knows about L1TF, right? Who was living under a rock for the past 1.5 years? You know what, at this point you don't want to know anymore. But has any one of you in your L1TF or in any updates seen this string ESX.problem hyperthreading unmitigated? Now, come on, raise your arms. Yeah, you should all be ashamed of yourself. Because if you've seen this, it meant that you didn't read the instructions. What does it say in the beginning? Update vCenter, you're right. Now this is a creative rendition by me. We don't have that in our official documentation, but I really argued we should have, because everyone forgets to update vCenter first. The string, so the language, the translation, the L18N for that string is in vCenter. ESXi has a definition of that error, but the actual language string is in vCenter, and hence why you never saw the translated version. vCenter first. Updates are getting easier, right? Come on. A little bit? Okay, updates are getting a little bit easier, so, and a little bit more reliable. At least in my job, I hear less people screaming about vSphere updates. Let's move on. So what does it mean? Well, L1TF is a problem where you can, in theory, side channel information out over a defect thanks to that's only available in hyperthreading. The cores have a shared cache, so you can cite, and the lines in the cache are not tagged, so any thread on the same core can read out the information in theory. And the side channel here allows that. So if you run with nothing, if you run with hyperthreading enabled and you run without this side channel aware scheduler, what you have is a host boundary, or how we call it. You can, in theory, if you manage to, I'm not sure how many people actually do manage, but if you manage to, you can get information from any process, from another process, depending on what your execution level is, obviously, from VM to VM and from ESXi to VM, right? So that's the boundary. Now, I would argue that it's not just a host boundary, it's also a VI boundary, because who here uses the same ESXi root password? Don't raise your arms, all right? Just smile and nod. Yeah, I know. Yeah, we lazy people, we understand each other. But in theory, if you have any shared information, that is obviously not optimal. Now, what we introduced in 6.7 update 2, and no, it will not be backported to any other ESXi version before that, we introduced the side channel aware scheduler V2, which basically now allows vCPUs of the same VM to execute on the same core. And now the boundary is within a VM. The VM cannot side channel information out of ESXi and not between VMs. Now, what you see though is that the processes inside of the VM obviously do not have a boundary. The only way to do that is using the side channel aware scheduler version 1, which is no hyperthreading. Well, no, it's not no hyperthreading. We don't turn hyperthreading off. We just don't use it. What's the difference, you ask? The difference is that the former sounds really bad and the later has plausible deniability. So here's the thing, right? The reason is that we use schedulers is that we want to make sure that you disable hyperthreading for the security risk. If it changes in future versions, microcode, CPUs, we want to make the best decision for you based on your requirement. If you disable it in the BIOS, we don't know whether you disabled it for performance reason or anything else. Hence, just use the schedulers based on your security requirements. So what's the performance impact? I am not going to go into the performance impact because that is a longer discussion, and we have a very, very detailed white paper that covers that. The only thing I want to show you is the default, obviously no hyperthreading, we don't use hyperthreading in the side channel array scheduler 1 and 2. And what I always want to highlight is in most white papers, we show you the performance or the performance impact when we have a VM that runs insanely hot at capacity, right? We're running it to 99% utilization. How many workloads in your environment run at 99% utilization? Oh, that's good. I'm happy for you guys. So what we can see on the right side is the reduced load consolidation. I don't quite remember what the exact percentage was, but this is a little bit closer to reality. So if you want to ask, can the SVA version 2 catch up on the performance gap I have because we don't have hyperthreading? And again, hyperthreading doesn't mean immediate performance impact. It means performance impact once you go over core capacity, right? So you go until 100, and then you don't have the 25. It's not really before that, right? So it's not an immediate performance impact. It's a capacity impact that happens at the end of the capacity because ESXi is scheduled on cores first and then on threads. Okay, so I want to keep this fairly brief because there's another NUMA session for about an hour. I'm going to link to that later. But let's talk NUMA briefly. If there's one thing you remember about NUMA topology, I want to make sure that we have the nomenclature right. So we all know what DIMMs are, right? Memory DIMMs. Banks of stuff with chips on it, we put them in, gives it memory. Perfect. Now, the thing next to it where you put the physical socket in is called a socket or a package, is what you also often see it referred to on ESXi. And usually, right, or very often, people would say that is a NUMA node, right? Yes, could be, but doesn't have to be. A socket or package equals NUMA doesn't happen, right? It doesn't have to be. You could also have 1 or 2 NUMA nodes per socket. AMD Opteron, right? They had 2 NUMA nodes per socket. If you enable, obviously going through, if you also have different scheduling domains. You have last level caches, you have dies. Zen CPU has what, 4 dies now? Zen 1? Last level cache domains, we're going to get into that in a second. But my point here being is that the physical representation of something and the topology doesn't always have to be the same thing. That's why we can configure them differently for VM. Now, also if you enable cluster on die or subNUMA clustering for Intel, you will also create 2 LLC domains and you will create 2 NUMA nodes per physical socket. So again, socket doesn't necessarily equal NUMA node. And there's a difference between NUMA topology and CPU topology and last level cache topology and so on. So why we're talking about this, let's zoom into CPU and look at the core components, right? We have a core, and a core owns L1 and L2 cache. The closer the cache, the smaller, the further away, the bigger. Now what we see here is that not the DRAM is the common cache, the common memory, it's actually the last level cache that can be accessed by all cores. And this is, just briefly, the L1 core usually the smallest but the fastest, and the further we go out, the bigger the cores are. Why does it get slower if it gets bigger? Well, one really good reason is, first of all, the cost of the cost of the specific memory technology, but also distance. Again, light speed in copper is like what, this? So if caches grow bigger, the further they're out. And the difference between the last level cache access and the DRAM access can be quite dramatic. So our scheduler also tries to schedule things in the last level cache, right? This is, by the way, where there were a few issues with AMD Zen 1 before update 2, I think 6.7 update 2, or because it kind of over-hoarded vCPUs in the last level cache domain instead of fully utilizing the whole NUMA node. In any case, so cache is important. Now, looking back about 10 years, what kind of systems did we have? Like, what did we play Quake 1 on, right? Or Counter-Strike 0.9. So in any case, so back then we had sockets, we had multiple sockets, and we had a NOS bridge, and the access from any socket to any part of memory was exactly the same speed. Uniform memory access, right? So that was all good and well, but the problem was obviously we have a bottleneck, and the CPUs got faster, the RAM got bigger, but RAM didn't really get much faster. So we kind of had to remove that bottleneck. And how that happened was NUMA, non-uniform memory access. Now we have a memory controller per CPU instead of in the NOS bridge. And that memory controller has preferred or closed memory. So if you have to access memory and the memory happens to be on the core next, you have fast access. Or if it's somewhere else, you can also get routed over other IMCs and QPIs to a different socket, or even around the corner, right? So obviously, the further you have to go, the longer the access latency is. But just because you're remote doesn't mean you're really bad or that your application is massively affected by it. It only matters if your application is latency sensitive to that memory access and if you have to do a lot of them, right? So there's tons of prefetching going on. So if you're very random, then you take that latency every single time. If you're reading in the same page, there's so much prefetch for you already, it's going to be in the cache before you want to access the next byte. So what I'm showing here is a measurement on all the, I forgot what it was. But it's about an 8-year-old CPU, and the measurement was done using IMC, Intel Memory Check. And you can see that the latency in nanoseconds, obviously the 72 nanoseconds directly on the socket, 290 on the socket next. So you might say, wow, so if I have remote memory or remote NUMA access, then I'm going to be 4 times slower? No. This particular host is 4 times slower. You will see also that when we go a little bit further around the corner, if we're routed, it actually doesn't get too much worse. Now, this is very specific to the CPU, to the layout, to the RAM being used, and the utilization. There's another example where you might have three QPIs per socket, and now you don't have to get routed, but what that also means is that now your local latency is only 136. So again, we went from a factor of 4 to a factor of 1.5. So just because you have remote memory doesn't mean you have a necessarily massive performance impact. It's all very dependent. There are some applications that are sensitive. There are some applications where they're not. If every application was sensitive to that, then we would have had a lot more bugs about our NUMA scheduler. No, I'm just kidding. I mean, it's all fixed by now, mostly. But it runs very well, and it's not necessarily critical. Okay, so what do we do with NUMA scheduling? We have this concept called NUMA clients. The NUMA client is let's say, the atomic unit of scheduling. It means a certain vCPU range and a certain memory range for that VM that we schedule. And first they're being placed round robin and based on capacity, and they have their memory that is close to their home node. How we balance these things is based on locality and load, right? So what does that mean? You start another VM, memory still fits, vCPUs get into each other's way, there's going to be contention, there's ready time. That means the VMs are now, or when the NUMA scheduler runs, is now looking for a better placement of a VM. So the VM gets balanced migrated to another socket because it's balanced to the CPU load. The memory will follow to wherever the home node is of that particular VM. So now the memory is being copied in the background while this is over there. Now, what could also happen is that the VM that was on the original socket migrates off because of DRS, or it's powered off or remote. Now, what can happen now? That the majority of memory that was still on that socket and the VM down there that still had to copy all the memory over says, you know what, your memory's still over there, why don't you go back, right? It's easier for us to copy the 200 megabytes back than it is to copy the 50 gigabyte down. So there's this called a balance or a locality migration due to memory locality because there's more memory somewhere else. And then there's load swaps and locality swaps, and there's about 6 different ones which are a combination of optimizing the load distribution across those nodes. And you don't want me to go into detail, I don't want to go into detail, but usually all of this works very well. The reason why I'm going into this, and this is how you get NUMA client stats on ESI with SCAT-stats TNUMA migrations, you can see that sometimes certain migrations called locality migrations are a little bit excessive. Sometimes you can see thrashing. Sometimes you can see that VM is a horde on a NUMA node and you have too much contention. So a locality migration also happens for what we call action affinity or a relationship, meaning if threads execute and they communicate, meaning they share a memory region, it would be best that these run on the same NUMA node, right? Let's say a netpol world and a vCPU and a VM. So sometimes we can over-migrate VMs for that relationship benefit, but we underestimate the CPU contention. And that can happen. That usually only happens on hosts that have a few larger VMs. If you have hosted many small VMs, not a big deal. A few large VMs can be a big deal. Check out this KB. It's something I encounter fairly often. So if anyone's saying, well, why is this NUMA node loaded and this isn't, or why is this VM migrating, that's probably going to be your answer. Okay, so you get the slides anyway. That's PDF export. So why these VNUMA decisions? What did we do and why did we do it? We had good reasons, right? So you remember in 6.5 we made a change in cores per socket, and why is this so complicated? What happened? In ESXi4 we had CPU-ID cores per socket. We introduced it for licensing reasons only, so that you could create a Windows XP VM and give it 2 sockets, because every single vCPU you add is a single core, single socket, right? So you're going over licensing restrictions fairly quickly. That's why it was introduced. In ESXi 4.1, we actually made it supported and put it into the GUI. In ESX.5, back then the maximum number of vCPUs was 8, right? That was it, 4.1, 8 vCPUs. So we've come quite a long way since then. In ESXi5, we introduced VNUMA. Everyone remembers that, right? And there, the maximum number of cores per VM was 32. So what did we do? We said, you know what? To be backward compatible so that we do not affect past VMs, we're going to set the VNUMA minimum limit. So how big does a VM have to be for the VNUMA sizing algorithm to actually happen? We set that to 9 because it couldn't affect any of the old VMs, right? But the reason, by the way, why we usually only NUMA size once is that particular applications, Oracle databases, get their NUMA, maybe not anymore, but they get the NUMA topology on installation. So if you shut it down, you change NUMA topology, and you boot it back up again, it's gone. It was one of 2 applications, but the more common one. So that's why we usually only do a VNUMA topology to the VM once. So the problem with this here is that we thought it was a good idea that you can set cores per socket, and if you set cores per socket, you obviously also have an idea behind that you can also set that vCPU max per virtual node option. That's what we thought. Well, the road to hell, right, is plastered with good intentions. Turns out that was not a good idea, and we kind of reverted that in 6.5. So why is that? Let's look at the NUMA node, the memory, and the CPU topology, and the VNUMA topology. And again, they're independent things. The only thing that connects them is that one decision we made where we connect the CPU topology to the VNUMA topology. If you create a VM, it has a cores per socket topology, right? That doesn't influence ESXi scheduling. It might influence Gesto as an application scheduling, and it might influence the cache topology that the applications can read, but it doesn't influence us. Then there is the VNUMA topology. We also call it the virtual proximity domain. Doesn't affect ESI scheduling. That's the NUMA topology we present to the guest, which will stay the same once it's being created, unless you touch any NUMA settings. And then there's the physical proximity domain, which is the NUMA client, the atomic scheduling unit. So here, the PPD is what we schedule. Now, what does auto-sizing mean? In theory, when you create a VM, and that is wide, and you have cores per socket set to 1, VPD will be sized automatically within the bounds of the underlying physical infrastructure. Now, what happens if we set cores per socket to something that's larger than what you see on a socket? Before 6.5, you would have also affected the VNUMA topology, not just the CPU topology. So the only thing we did in 6.5 was to separate this so that if you set a wrong CPU topology, you don't also set a wrong VNUMA topology, because the latter is usually more important for application performance than the former. But it can also be important. Now, wouldn't it be nice if there was automatic cores per socket? Well, I'm not saying anything, right? I'm just saying it would be nice. Okay. So again, in 6.5 we changed that. So now if you set cores per socket, it won't affect the VPDs anymore. So again, there's a difference in sizing and scheduling, and they're distinct from each other. Sizing usually happens once, scheduling happens all the time. Sizing happens once until you touch another option. And if you want to hear Frank talk about this for 1 hour, he's up on Thursday. Session gets, obviously, probably is already full, but it's a very good comprehensive overview of VNUMA topology and CPU topology. Ooh. Give me a second. Who else is out of breath? Is it as hard to follow as it is hard to speak? Okay. Extreme performance. It's on my shirt. It's on the agenda. It's the name of the session. But what about extreme appropriate performance? Do we always need all the room? Do you drive to work in a drag car, a drag racer car? Obviously you don't, right? So if we look at the HBI25 client, and everyone here loves the HBI25 client, right? Yay! Okay. That was a little bit better when it was newer. You probably already forgot all the pain you had before with NGC. Again, by the way, NGC was really just deployed to make you all learn PowerShell. It worked. So let's look at the HTML5 client, and we see our VMs here. And when we look at our VMs, we think that at least most of them are like highly tuned precision Formula One engines that do their job and they do them as fast as possible, and we want them to succeed and run as fast as possible. But that is not what most VMs are. No, non-tier 1 VMs. Most VMs are closer to a price cap, right? You want to get from A to B in a certain time for a certain cost. You don't want to pay $200 for a ride to the airport that takes 15 minutes instead of 20, right? So overtuning is a thing. And usually when you come to these sessions, we tell you how to overtune. And we want to try to be a little bit more sensible about that for multiple reasons. So we usually, when VMware tunes their default, we're assuming this Maslow pyramid of needs, right? Everyone knows the Maslow pyramid, right? Rest and shelter, and then at some point fulfillment in life, as if that ever happens. So we have stability as the main need for VMs. Then we usually have security, performance, and consolidation. But sometimes you want to make decisions to maybe get a little bit less performance, but much more consolidation, because it's not always in the same range. So you want to consolidate a little more, maybe even want to sacrifice a little bit of security for performance or consolidation. It's perfectly possible. So but our defaults are like that. So there is no reason not to consolidate and to be more efficient, right? I mean, besides maybe a tiny little bit of performance impact. So but in theory, if we could consolidate without a performance impact, it would be perfect, right? You want to run as tight as humanly possible to be effective, to be cost effective. And one reason why we want to do that is obviously sustainability, right? You probably read the news, you know what's going on. It's pretty warm here, isn't it? So especially for November. But I mean, there's a different reason, right? There's also cost. If you're okay with this temperature and you just want to save money, that's perfectly fine as well. It's the same outcome. Whether you do it for cost or you do it for other reasons, doesn't really matter. We want to drive efficient and together while still being performant as we need. So this was actually when I went to VMUG in Frankfurt, and I was traveling for about 6 hours, and I flew with British Airways. We offset our CO2 for that, by the way, so VMware pays for that. We went to Cap Europe, and I stayed at the Hilton, and all three of them had sustainability somewhere directly in my face. I actually had talks with people that want to be more sustainable and more energy efficient. I was like, why? Do you want to save on your power bill? We don't care about the power bill. The flat rate is paid by someone else. We want to say that we're sustainable. Yeah, it's a very common, or it has been a very common motivation over the past few months and years. The most recent example, I'm staying at a hotel. This was right in the door. Didn't say ring this bell for the concierge, it says we're energy efficient. So again, this is something that people advertise with, and it's something that's going to become more interesting and more important in the future. So eat your cake and have it too. Well, what you're saying, oh, I want to consolidate, but I want performance and there's risk involved. So is there something I can do to have my cake and eat it too? Well, maybe there's, and I hope I can talk about that. But what we need first, what does every good technology need when it starts out so it gains traction? A mascot, right? No? I worked for other products, come on. So I took the most beloved superhero there is. No one? Captain Planet? Captain effing Planet? Love, Earth, Wind and Fire, whatever it was. That was the only series that would run when I was sneaking down at my parents' house at 6 o'clock in the morning. So no Superman, just Captain Planet. But Captain Planet together with the beloved Melvin, the mascot for super VMs. And don't blink, right? And together, they become Yeah. Captain Melvin, thank you very much. That was a flight from London to San Francisco. It was about 9 hours. It's original art, nothing is stolen. Okay, so how can we help Captain Melvin to run resource effective but also performant? Well, you don't run it. You turn off stuff that you don't need. Do you know how many zombie VMs you have? Well, if you would have turned them off, but you should really try to investigate that. When VMware moved data centers, there was a massive percentage of VMs that we just shut off. Nothing. Scream tested, right? No one screamed, not a whisper. That's how the world ends, right? So it's a lifecycle optimization. We're not going to talk about that, but you want to figure out which VMs you really need, who the owners, and whether you need to run them. Use distributed power management. At least here no one is laughing. We're actually going to work on that so you don't get fired when you use it. But really you should use it, and there's a few things you can do for that. What you can also do is you can run it as efficiently as possible, right? And that means use low-risk power management, use deep C states, which enable you to run faster and save energy, use transparent page sharing. What, I thought that was dead. It's not dead, and that's what we're going to talk about. And you could also right size. But right size is a problem because if you're right size, you have to talk to users, and who likes that? Sorry, maybe it's just my perspective. But the right sizing is an operational investment. I don't know how many VMs you could just reduce the memory to without talking to someone. And was that fun? Hey, I'm going to take 8 gigabytes of memory because you don't use it. Come and get it. Okay, so a few questions, right? A little bit of participation, so I can take that back to our product department. Do you overcommit memory? ARMS.
For what?
Okay. Do you overcommit memory in production? That's not many ARMS, if you can see that, by the way, if you turn around. And what's your ratio? Don't tell me your ratio. The reason I'm asking this is because we asked the same question in 2008. And there, the answer was 60% overcommit. 90 of those overcommit in production, and the ratio was on average and mean 1.8. 1.8. It's nearly a factor of 2. Who you overcommit with a factor of 1.8? Memory. Yeah, that's what I thought. So why is that? Why don't we overcommit? But first, let me ask you a question. If you have a button that you could click and you would automatically reclaim memory that you didn't know you had, but it might impact the performance and don't really know how much, but you could easily reverse it, would you press the button? Come on, we're in IT. Don't tell me you have never pressed a button that you didn't know what it did. Okay. No, this is 2 ARMs here. I don't have to take a picture of that. I can count that. So, transparent page sharing, quick recap. Transparent page sharing still runs constantly. It's not off. It runs 4 VMs. It still runs in the background. It doesn't work in between VMs anymore, but for the same VM, it's still happening. So it runs. There's a pshare thread that calculates caches. It doesn't cache or doesn't share guest large pages. It hashes small pages in ESXi large pages, which is important because we back with ESXi large pages by default, VM to host. But we don't share them. They're only hashed, they're not shared. When are they shared? When we have to. When do we have to? Not very often. Or well, in that maybe for some of you, but most people probably don't overcommit memory too much, as just seen by the recent show of hands here. And large pages are broken at clear. That's since 6.0, but I'm going to get into that. By default, they're NUMA local. So every NUMA node has a copy of that copy on the right page. And again, as I mentioned before, for the past few years, due to some security changes, only within a VM, not between VMs anymore. And the 0 page is the most common. That's going to be important later. So, what happened over the past few years? Why are we in the position that we're in? Page shared went down. When I started at VMware, I could throw hundreds, it felt like, Windows 2003 VMs on a host, and memory consumed would tick up millimeter. Everything was just running fine, and I could overcommit massively. In the same time, memory consumed went up, and a bunch of things happened. It was not just one thing, and that's what makes it complicated. It was a bunch of things that happened at the same time that all impact this. One was the technology change, so nested page tables, or EPT enhanced page tables, meaning now the CPU can do the page walk instead of having to rely on shadow page tables. Host large pages to combat a certain certain latency overhead because of that. Rowhammer, the security reason. Windows caching. So Linux always was caching aggressively, but now Windows actually started to cache files a little bit more aggressive. Instead of flushing them out, if you opened the file, it remained in cache. And what is cache? Pretty damn unique to a VM, so you cannot easily share it. And then also Linux introduced transparent use pages, which made it a little bit harder. In the same time, what happened? Ballooned memory went up, and swap went up as well. Because people overcommitted, the technology changed under their feet, they replaced the host, all of a sudden, damn, I'm down from 1.8 to 1.2. How did that happen? Well, one big reason of that was large pages and the associate handling of it. So what we do when we reach min-free, which is like 3 to 5%, 3-ish, 5 maximum of memory, when we reach that, only if you had like 95% memory consumption plus for most hosts, will we reclaim memory. And first, we balloon, then we compress, we swap, and we block. We always share, right? That was everyone remember. TPS is always on, we always share. It's a damn dirty lie. And it's a dirty lie because everything is backed by large pages, and large pages can't be shared, so transparent page sharing is none. Meaning, you only break those down once you reach the high state. We recognized that, and we fixed it. We introduced a clear state that is 3 times as big as clear state is 3 times as big as the min-free, so that large pages get broken down sooner. Imagine that. Imagine you have a runway and you have a stopway. You know, where the plane can roll out in case anything happens? Usually a fairly small amount. Now let's translate that to ESX, right? And we see back in the back there's clear min-free. This is how much memory you have to consume before we reclaim memory from other VMs. And this is at a host level, no per VM or resource level. Now let's translate that. If you roll on the asphalt on the stopway, you have TPS, not really much of an impact. And then you balloon out, 0 pages stand by, not much of an impact. And then you go into ballooning out the working set, and to swap, that's terrible. Like the gear collapses, the wings break off, front felts off, it's terrible, terrible. You don't want to go there, right? But you can still drive in TPS and available balloon. There's not much of an impact. The problem is, what if it looks like this? What if you don't know how big that TPS range is that you have to your availability? What is that? 95% consumed. What is this? 95% consumed. And this over here, I'll give it away because I don't have time, 95% consumed. So the main metric that many people are looking at when they do capacity planning is consumed memory, and you don't really know the what if, what do I have available and what is the cost, which is something that I'm trying to get to in the next 4 minutes. So transparent page sharing has a transparency problem, right? And that's hard, and that's really not immediately available to you. So why do we do that? Why do we do large pages if it makes things so complicated? And the reason is performance. When you have a process, and I have multiple processes, you have not just one process, you have multiple processes, right? These processes all have a singular, contiguous, complete address space of 256 terabyte. And that somehow, via magic, which is good enough for me, has to be translated to less terabyte of physical memory and some swap space. Now, how do we do that? Again, magic. And that magic has a certain cost. Like all magic has a cost, right? Oh, that's nice. I'm going to remember that. And now we abstract. We have more than one VM. We have multiple VMs. Does multiple VMs have a certain max size? That max size somehow has to translate to a finite space of memory, although we have different technologies to present that physical memory or represent whatever that memory is. We have transparent page sharing, we have zip, we have ballooning. So why are we doing this? Because we have to translate addresses. And when you translate an address from virtual to physical, you have to translate the address, but the offset stays the same. So the bits in the address is what defines the cost of translating that address. The offset, which is the page site, always stays the same. Now, if you have to translate that, you have to do multiple memory accesses to go from one table to another table, from another table to another table. The bigger your page, the fewer of those accesses you have to make. And you think that's complicated? Well, this is bare metal. Once you talk virtualization, it looks like this. And for every virtual to physical, you have to do a physical to machine. So this and this and this and this and this and this. And that can be quite costly. Now, the reason we use large pages is if you disable large pages or if you enable large pages in a guest, it takes away the last bit. If you take it away if you set large pages on the host, we're here. And that reduces the maximum overhead. Now, obviously, there's a lot of caching in here, and that is the worst case scenario, but we want to reduce that overhead. Now, you're asking me, how often do I take that overhead? Because we already learned that an overhead is only as bad as depending on how often I take it. Well, my argument is, and we have 1 gigabyte pages as well. I forgot to say that. 6.7, hardware version 14, 1 gigabyte pages. How bad is that benefit? Let's skip back to the example of the landing strip. The problem is that this tells you how much memory is available. But if you turn this around, right? So this is memory consumed, but it also tells you how much is available. If you turn this around, it kind of is like a fuel gouge where you go down and it stops at red. Imagine you're driving on the road and it stops and you have 50 kilometers to go and it stops at red and it stops moving. And you continue 50 kilometers, 100 kilometers, and you're still in the car and it doesn't go further down. You call support. They don't know. Documentation, it's crap. So you figure out at some point that the car manufacturer implemented something that lets you run in less and less and less gas until the car stops. You wouldn't do that, right? Because the transparency just isn't there, but that's what we currently have for transparent page sharing. What I'm saying is that the performance impact from most VMs is probably as little or even below 5%. There's a few VMs you should never ever do disable large pages, but you can preemptively disable them on many workloads and just have that TPS memory within a VM available before you have to overcommit your host or before you reach that 95% mark. So for anything that isn't super critical, you can set that option. If you want to go to GitHub v10, there's a little script in the folder sowas von unsupported that gets the amount of memory that you can share if you would break down large pages. So this is the what is in it for me. And in a few weeks or so, I'm going to publish a few more scripts that do it a little bit more elegant than that and do the collection for the whole thing. GitHub v10. And again, you get the recording. So you can disable it per VM, you can disable it per host, and you can check whether it worked. So I'm asked one more question, even though I'm a little bit over time. Would you press that button now? Would you press the button if you knew what was in it for you and if you can approximate that there wouldn't be a performance impact? Would you have the desire to have consumed represent what you can share, or a metric that represents what you can share instead of being, let's say, in comparison to not knowing how much memory you still have to give? Would you press that button a little bit more likely than before? Come on, this is my job. A few arms. Thank you very much. Here's the thing, right? What I need this to go back to product engineering to tell them that there is a certain interest and that we should develop something that makes this easier. So, with that being said, Captain Melvin wants you to either save the planet or money. I don't care. It's the same result. Whatever floats your boat. Well, I care, right? But if you don't care, you can save money as well. And I don't know how long we have Captain Melvin because it's cease and desist happen. So with that, please fill out your survey. There is more presentations, by the way, you can go to. Go to the Extreme Performance series. They're all in the app. Fill out our survey. VMware Go Perf is a different survey than the session survey. We would still very much like if you do that too. Fill out the main survey. And thank you very much.